Once we have an LCD, whether we're dealing with fractions or rational expressions, we then have to find equivalent forms of those fractions or rational expressions where the denominator is the LCD. So what we do is we obtain an equivalent expression by multiplying the numerator and denominator by a well-chosen 1. Okay, so we're looking for what would I multiply my denominator by so that my denominator becomes the LCD. But then whatever I multiply my denominator by, I have to then multiply my numerator by that same value because that gives us a weird or a well-chosen 1. Okay, so let's look at an example with just numbers. Let's say I had 2/3. And let's say I needed my denominator to be 12. So let's say 12 was the LCD. We were starting with 2/3. What would I multiply 3 by to obtain the LCD of 12? Well, I would have to multiply my 3 by a 4. But I can't just multiply part of my fraction by some value. It's no longer equivalent. I have to multiply both parts of my fraction by that same value. So I would then multiply my numerator by that same 4. Well, what would happen then is if you look at this, we multiplied the numerator by 4, we multiplied the denominator by 4, and 4 divided by 4 is a well-chosen 1. 4 divided by 4 is 1. So even though we're going to change the appearance of the fraction, we're not going to change the value of the fraction because when we multiply by 1, we don't change the value. So that's essentially what's happening here. If we have the rational expression P over Q, and we want to get an equivalent form of that, we need to multiply P over Q by some version of 1. Well, if we can multiply P over Q by R over R, where R is a polynomial, we will then get P over R times Q over R, which is an equivalent form of the initial P over Q because R over R is equal to 1. So we're definitely going to change the appearance of our rational expression, but we're not changing its inherent value, okay? So essentially multiply the numerator and the denominator by the rational expression. We're going to multiply the numerator and denominator of the rational expression P over Q by the polynomial R that will make the denominator equivalent to the LCD. So let me say that one more time because I got a little chopped up there. We're going to multiply the numerator and denominator in our rational expression, which we're calling P over Q. We're going to multiply both parts of that rational expression by the polynomial R. And that polynomial R is the polynomial that forces my denominator to be the LCD. Okay, so again, a lot of times when you see it in words, it doesn't make as much sense, but when you see it in practice, it kind of comes together. So let's look at example 3. So in example 3 here, it says find an equivalent rational expression using the provided LCD. So for part A, we want to rewrite 4 over x plus 5 using the LCD of x plus 4, x plus 5. So we want an equivalent form of 4 over x plus 5 using that LCD. So we start with 4 over x plus 5. And we want an equivalent form where the denominator is x plus 4 times x plus 5. So we start by asking ourselves, what would I multiply my denominator of x plus 5 by to get the LCD of x plus 4 times x plus 5? Well, what's missing from our initial from our initial denominator that is part of the LCD is x plus 4. But here's the thing, if I multiply the denominator by x plus 4, I have to multiply the numerator by x plus 4. And remember, anything divided by itself is really just 1. So we're really multiplying 4 over x plus 5 by just some weird version of 1. We're not changing the value of 4 over x plus 5. We're merely changing its appearance to make it useful to us. So our new numerator would be 4 times x plus 4. And you could leave it just like that. That would be the equivalent expression. Or you could go further and say it is 4x plus 16. Please do leave the denominator factored, though. You don't have to worry about multiplying out the denominator. And there you have it. That's your equivalent expression, okay? So this x plus 4 over x plus 4, this is like the R in that previous description that we had of finding an equivalent expression. All right, for the next example, part B, we have rewrite 3x over x minus 2 using the LCD x plus 2 plus x, or x plus 2. Bless my heart. We're going to use the LCD of x squared plus 5x minus 14. I don't know where the x plus 2 came from. Okay, so what we need to do now is factor x squared plus 5x minus 14. When we're dealing with LCDs, it's much easier for us if they're in their factored form because then we know what factors we need to multiply by to get the LCD. So let's factor this. Luckily, we have a quadratic trinomial where the coefficient on the square term is 1. That makes the factoring that easy shortcut factoring. We start two binomials. We're looking for basically factors of x squared, so we're going to get factors of x and x. So that's the first term in each binomial. Next, we're looking for factors of negative 14 that have a sum of 5. So numbers that multiply to give us negative 14, but add to give us 5. So we could use negative 14 and 1, 14 and negative 1, negative 7 and 2, or 7 and negative 2. So which of those pairs of factors adds up to be 5? Well, 7 and negative 2. So I'm going to fill in plus 7 and negative 2. So now when I look at my initial denominator and compare it to the LCD, it's easy to see what factor is missing, okay? So I'm going to take my 3x over x minus 2, and I'm going to determine what I would multiply it by so that I get the LCD. So looking at my initial denominator, what is missing from the initial denominator compared to the LCD? Well, it's the x plus 7. So I'm going to multiply my denominator by x plus 7. But if I multiply the denominator, I have to also multiply the numerator to keep this in equivalent form. So this right here in blue is my r, and it's some weird version of 1. X plus 7 divided by x plus 7 equals 1. So when I go to multiply across, I would just get 3x times x plus 7, and this becomes my equivalent form. So this is the equivalent expression. Now, with the denominators, you just leave the denominator factored, but for the numerator, when adding and subtracting, you could go ahead and multiply across. So we would get 3x squared plus 21x all over x plus 7, x minus 2. And there you have it. So now we've seen the two main components of what we're going to need to do to prepare for adding and subtracting rational expressions. We have to find an LCD, and then we have to be able to find equivalent forms of that rational expression. Once we get those equivalent forms, we can then proceed with adding and subtracting.